Morning, dear students. Today we'll talk about strain displacement relations. So we are talking about finite element method, wherein some preliminary content that you want to understand the finite element method is the prior knowledge from theory of velocity. So where you need to learn the strain displacement relations. Okay, so here we are. So let us consider a particle where its dimensions being say dx and dy. Yeah, the same particle after the load application is going to deform in this fashion. Okay, so let this be the deformed shape. So name this element A, B, C, D. Let it be A dash, B dash, C dash, and D dash. Okay, so this is x axis, y axis. Let us say this A dash is at u displacement from A. Okay, so from A dash is at a distance u. So this is u displacement, x directional displacement. Same way, in y direction, this is v. Okay, so x displacements, as you know, in the previous session we have talked about. We denote u as x displacement and v as y displacement. Okay, yeah, now drop this point, okay, onto the horizontal line. Name this as v double dash. Okay, so by definition, strain is equal to change in length by original length. Okay, see, original length was AB, so that is denominator. Here you need have change in length. So what is the change in length? AB in horizontal direction. So here you see the horizontal dimension is A dash B double dash. A dash B double dash is the final length minus initial length is the change in length divided by original length. Okay. So you know AB value, that is dx. Okay, where AB is equal to dx. Okay, so if you know A dash B double dash value, then you can estimate this strain value. Okay, so as you are looking at x direction, you see, so I name this as epsilon x. So now to write A dash B double dash value, okay, let us see. As A moved to A dash, B also moved to B dash. Okay, so what it could be? Okay, what will be this value? Okay, if AB is equal to A dash B dash, okay, we say is rigid body deformation, right? Rigid body. So as we talk about the deformations, okay, so we say it is not equal to A dash B dash. Okay, so which means there is strain in the body. Okay, so AB now is A dash B double dash is not equal to AB. Okay, now see in x direction, okay, for every dou x distance, say dou u is the deformation. Okay. So now in a length of dx, how much is the deformation, total deformation? Okay. So for dx length, right? So dou u by dou x, okay, per unit length, okay, into dx is the total change in length, right? So this is total change in length, right? So now initially it has moved to u, okay, plus this is the change, dou u by dou x into dx. So this is the final length, okay, right? So it's from here, a final displacement from b till b dash. This is the dimension. So now you want a dash b double dash value. So from here, this is the total length minus this u. If you do, you will get this, okay, a dash b double dash value, which means dx plus u plus dou u by dou x into dx. Okay, right? So this is total distance minus u. Okay, so this is a dash b double dash value. As u cancels out, it is simply dx plus dou u by dou x into dx. Okay, so now you substitute this a dash b double dash value into this expression. So let us see what we get. So epsilon x is equal to now a dash b double dash final length minus initial length divided by initial length. So what is this value? It is dx plus dou u by dou x into dx minus ab means dx divided by ab means dx. So you cancel out this dx. So dou u by dou x into dx divided by dx. Okay. So this dx cancels out. So what will remain is dou u by dou x. So the strain in x direction, epsilon x is equal to dou u by dou x. Okay. Similarly, in y direction, you can develop the same relation. So we call it as epsilon y, dou v by dou y. Okay. And for z direction, this is for y direction. Okay. Yeah, for z direction, epsilon z is equal to dou w by dou z. Okay. So now these are the strain displacement relations in normal direction. Strain displacement relation, strain displacement relations. Okay, so strain displacement relations in normal direction. Okay, so which means epsilon x dou u by dou x, epsilon y which is dou v by dou y, epsilon z dou w by dou z. So these are the strain displacements for normal strain. Okay. Now let us see for shear strain how to relate shear strain and displacement relations. Okay. Yeah, we consider the same diagram. Let us see the same picture. Okay, so shear strain is defined as when you pick two right angled lines. Okay, what will be the change in the angle? So this is initial angle, right angle, the final angle. So this minus this means what? This plus this. So which I call this as say theta 1. Let us say this is theta 2. Okay. So let us have a fresh diagram so that it will be much clear. Okay. Yeah. Same xy plane. Consider this. Yeah. Let us pick the element. Okay. Right. Then go with deform shape. Yeah. Now A dash, B dash, C dash. I call this as say theta 1. This I am calling it as theta 2. Okay. Now see here. This height. Yeah. I have defined this as V, right? If you recall, V. Okay. Now this value, you see, for every dou u, so each division, like if you make this dx into so many minute divisions, those I call them as dou x. Okay. So for every dou x, there is vertical displacement. Okay. See here, right? So which means vertical displacement is dou v. Okay. So at what rate? It is dou v by dou x. For every dou x, there is dou v value present here. So what will be this value? Okay. So this is v, this total value I'm writing now, plus dou v by dou x, the rate of the displacement, vertical displacement, multiplied by the distance, for what distance it is happening. Okay, so this is this b dash b double dash value, this one is b dash b double dash value. Okay, right? So now if I write tan theta 1, opposite side b dash b double dash, okay, divided by adjacent side a dash b double dash. Okay, this is a dash b double dash. So this angle I try to calculate. So b dash b double dash value, this, okay, dou v by, from the above expression, dou v by dou x into dx divided by this we have already calculated. A dash b double dash is equal to, see, this a dash b double dash is equal to dx plus dou u by dou x into dx. Okay, so that you substitute it here, dx plus dou u by dou x into dx. Okay, now so you see tan theta 1, take dx common from denominator, dou v by dou x into dx. So dx is common, 1 plus dou u by dou x. So dx goes. If you observe the denominator, it is 1 plus dou u by dou x. So this quantity is very much negligible. This is negligible. Okay. So 1 plus any negligible number is equal to 1. So this will become dou v by dou x divided by 1. So finally, tan theta 1 is nothing but dou v by dou x, where for this small angles, So this small angle, because you are talking about a particle, not this of this is just exaggerated. So you are talking about a particle. So this will be nothing but theta 1. Okay. So finally, your theta 1 value to v by dou x. Similarly, if you look at theta 2 calculation, okay, this value is nothing but, see, for every dy, this is dy, for every dou y distance, there is u displacement happening, horizontal displacement. Okay, so at a rate of dou u by dou y. Okay, so this is the rate of displacement happening. So this value is dou u by dou y, okay, into dy. So similarly, if you go on work out, okay, like that, so the same thing you are going to get. Okay, so theta 2 I can write comfortably, it is dou u by dou y, the rate of the horizontal displacement happening in this direction, okay, vertical direction, right? This vertical side is deviating at a rate of dou u by dou y. Okay, so now the total change in angle theta 1 plus theta 2 is equal to dou v by dou x plus dou u by dou y. So this is nothing but shear. Yeah, as we are in xy plane, you can write gamma xy. So this is shear strain displacement relation. Similarly, for other planes also you can generate like gamma y z if you want to generate dou v by dou z plus dou w by dou y. Gamma zx you want to generate like dou u by dou z dou w by dou x. So these are the relations. Okay. So now we have got total 6 relations of strain displacement. So strain displacement relations both in normal as well as shear directions, like epsilon x is equal to dou u by dou x, epsilon y dou v by dou y, epsilon z dou w by dou z. These are normal strain. Shear strain dou u by dou y, dou v by dou x, yz dou v by dou z, w by dou y, zx dou u by dou z, w by dou x. These are called strain displacement relations. Okay, so this content is from actually theory of velocity, which is very much needed for finite element method. Okay, right, thank you.